It is not acceptable for a feeder to have only phase and neutral wires without a ground wire. This violates National Electrical Code sections 250.112 and 250.138. An equipment grounding conductor, or EGC, is required for protection and bonding of metal raceways and enclosures. It can be run on the exterior of a liquid-type flexible metal conduit, or LFMC, and terminated on the switchboard end of the conduit. National Electrical Code section 250.120c requires protection for equipment grounding conductors smaller than number 6 American wire gauge, or AWK. This can be achieved by using a metal raceway as the equipment grounding conductor, which is the case with the liquid-type flexible metal conduit. AC cable is a type of armored cable that includes both phase and neutral conductors as well as an equipment grounding conductor. It can be used as an alternative to running separate conductors on the exterior of the liquid-type flexible metal conduit. AC cable is more flexible and easier to install than running separate conductors. It also provides protection for the equipment grounding conductor. The best solution is to have the contractor install an equipment grounding conductor on the exterior of the liquid-type flexible metal conduit and terminate it properly at the switchboard and the conduit. This will ensure proper grounding and bonding in accordance with the National Electrical Code. Now let's delve deeper into the specific National Electrical Code requirements and best practices for grounding and bonding electrical systems, particularly when dealing with situations where a feeder lacks a dedicated ground wire and utilizes liquid-type flexible metal conduit. The absence of a ground wire in a feeder is a significant safety concern and a violation of the National Electrical Code. Grounding and bonding are essential for providing a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices such as circuit breakers or fuses, and minimizing the risk of electrical shock. National Electrical Code sections 250.112 and 250.138 outline the requirements for equipment grounding and bonding, emphasizing the need for a complete and effective ground fault current path. An equipment grounding conductor is the conductor used to connect the non-current carrying metal parts of equipment, raceways, and other enclosures to the system grounded conductor, the grounding electrode conductor, or both, at the service equipment or source of a separately derived system. In the situation where a feeder lacks a ground wire, an equipment grounding conductor must be installed to ensure that metal raceways and enclosures are properly grounded and bonded. One acceptable method for providing equipment grounding in this scenario is to run an equipment grounding conductor on the exterior of the liquid-type flexible metal conduit. This equipment grounding conductor must be sized appropriately based on the rating of the overcurrent protective device protecting the circuit, as specified in National Electrical Code section 250.122. It is crucial to terminate the equipment grounding conductor properly at both ends of the liquid-type flexible metal conduit run. At the switchboard or source end, the equipment grounding conductor should be connected to the grounding bus or terminal bar. At the conduit end, the equipment grounding conductor should be connected to the metal enclosure or equipment being served. Proper termination techniques, such as using listed connectors and ensuring tight connections, are essential for maintaining a low impedance ground fault current path. National Electrical Code section 250.120c addresses the protection of equipment grounding conductors smaller than number 6 American wire gauge. This section requires that these equipment grounding conductors be protected from physical damage. In the case of an equipment grounding conductor run on the exterior of liquid-type flexible metal conduit, the conduit itself provides a degree of physical protection. However, it is important to ensure that the equipment grounding conductor is securely attached to the conduit and protected from abrasion or other forms of damage. If the equipment grounding conductor is exposed to physical damage, it may be necessary to provide additional protection, such as enclosing it in a non-metallic conduit or using a larger size equipment grounding conductor. An alternative solution for providing equipment grounding in this scenario is to use AC cable. AC cable, also known as armored cable, is a type of cable that includes phase conductors, a neutral conductor, and an equipment grounding conductor all within a flexible metal jacket. AC cable is a listed product and is permitted for use in accordance with the National Electrical Code. When using AC cable, the metal jacket serves as the equipment grounding conductor. It is important to ensure that the metal jacket is properly terminated at both ends of the cable run using listed connectors. AC cable offers several advantages over running separate conductors on the exterior of liquid-type flexible metal conduit. Firstly, AC cable is more flexible and easier to install, particularly in tight spaces or where there are numerous bends in the run. Secondly, AC cable provides inherent protection for the equipment grounding conductor as it is enclosed within the metal jacket. Thirdly, AC cable simplifies the installation process as all the conductors are contained within a single cable assembly. However, AC cable also has some disadvantages. Firstly, AC cable can be more expensive than running separate conductors. Secondly, AC cable may not be suitable for all applications, such as those where the cable is exposed to corrosive environments. In summary, when dealing with a feeder that lacks a ground wire and utilizes liquid-tight flexible metal conduit, there are several acceptable methods for providing equipment grounding. Running an equipment grounding conductor on the exterior of the liquid-tight flexible metal conduit is a common and effective solution. Alternatively, AC cable can be used to provide both power and equipment grounding in a single cable assembly. Regardless of the method chosen, it is essential to comply with all applicable National Electrical Code requirements and to ensure that the installation is performed by qualified personnel. Now, let's expand on the practical considerations of installing an external equipment grounding conductor on liquid-type flexible metal conduit. The selection of the appropriate size equipment grounding conductor is paramount. National Electrical Code Section 250.122 provides tables that correlate the size of the circuit or overcurrent protective device to the required size of the equipment grounding conductor. For example, if the feeder is protected by a 100-amp circuit breaker, the minimum size equipment grounding conductor required is number 8 American wire gauge copper or number 6 American wire gauge aluminum. It is crucial to consult the National Electrical Code tables and select the appropriate size equipment grounding conductor for the specific application. The material of the equipment grounding conductor is also an important consideration. Copper is the most common material used for equipment grounding conductors due to its excellent conductivity and corrosion resistance. Aluminum is also permitted, but it must be sized larger than copper to achieve the same level of conductivity. When selecting the material, it is important to consider the environmental conditions to which the equipment grounding conductor will be exposed. In corrosive environments, copper conductors may need to be protected with a corrosion-resistant coating. The method of attachment of the equipment grounding conductor to the liquid-type flexible metal conduit is also critical. The equipment grounding conductor must be securely attached to the conduit at regular intervals to ensure that it remains in close proximity to the conduit and provides an effective ground fault current path. One common method of attachment is to use cable ties or clamps that are specifically designed for this purpose. These cable ties or clamps should be made of a non-metallic material that is resistant to ultraviolet radiation and other environmental factors. The spacing between the cable ties or clamps should be sufficient to prevent the equipment grounding conductor from sagging or becoming detached from the conduit. Another method of attachment is to use metal struts or clamps that are bonded to the conduit. This method provides a more robust connection, but it is important to ensure that the metal straps or clamps are made of a compatible material to prevent galvanic corrosion. The termination of the equipment grounding conductor at the switchboard or source end is also critical. The equipment grounding conductor must be connected to the grounding bus or terminal bar in the switchboard. The grounding bus or terminal bar should be sized appropriately to accommodate the equipment grounding conductor and should be securely connected to the built-in grounding electrode system. The termination of the equipment grounding conductor at the conduit end is equally important. The equipment grounding conductor must be connected to the metal enclosure or equipment being served. This connection should be made using a listed connector that is specifically designed for this purpose. The connector should be installed in accordance with the manufacturer's instructions and should be tightened to the proper torque. When installing an external equipment grounding conductor on liquid-tight flexible metal conduit, it is important to follow all applicable safety precautions. Firstly, the power to the circuit should be de-energized before any work is performed. Secondly, appropriate personal protective equipment, such as gloves and safety glasses, should be worn. Thirdly, all tools and equipment should be properly grounded. By following these safety precautions, the risk of electrical shock or other injuries can be minimized. Now let's examine the alternative solution of using an AC cable in more detail. AC cable consists of insulated conductors enclosed in a flexible metal armor. The metal armor serves as the equipment grounding conductor and provides physical protection for the conductors. AC cable is available in a variety of sizes and configurations to suit different applications. When using AC cable, it is important to select the appropriate size and type of cable for the specific application. The size of the cable should be based on the ampacity of the circuit and the voltage drop requirement. The type of cable should be based on the environmental conditions to which the cable will be exposed. When installing AC cable, it is important to follow all applicable National Electrical Code requirements and the manufacturer's instructions. The cable should be supported at regular intervals to prevent sagging and to protect it from physical damage. The cable should be terminated using listed connectors that are specifically designed for AC cable. The connectors should be installed in accordance with the manufacturer's instructions and should be tightened to the proper torque. One of the advantages of using AC cable is that it is relatively easy to install. The flexible metal armor allows the cable to be bent and routed around obstacles. The cable can be cut to length and terminated using simple hand tools. Another advantage of using AC cable is that it provides excellent protection for the conductors. The metal armor protects the conductors from physical damage, moisture, and other environmental factors. However, AC cable also has some disadvantages. Firstly, AC cable can be more expensive than other types of wiring. Secondly, AC cable can be more difficult to work with in tight spaces. Thirdly, AC cable may not be suitable for all applications, such as those where the cable is exposed to corrosive environments. In summary, when dealing with a feeder that lacks a ground wire and utilizes liquid-tight flexible metal conduit, both running an external equipment grounding conductor and using AC cable are acceptable solutions for providing equipment grounding. The choice between these two solutions depends on the specific application and the preferences of the installer. Regardless of the solution chosen, it is essential to comply with all applicable National Electrical Code requirements and to ensure that the installation is performed by qualified personnel. Let's further elaborate on the code compliance aspects and potential pitfalls to avoid during installation. Compliance with the National Electrical Code is not just a recommendation, it's a legal requirement in most jurisdictions. Ignoring code requirements can lead to safety hazards, equipment damage, and legal liabilities. When installing an external equipment grounding conductor, ensure that the conductor is properly sized according to National Electrical Code Table 250.122. Undersized equipment grounding conductors can limit the flow of fault current, potentially delaying the operation of overcurrent protective devices. Also, ensure that the equipment grounding conductor is securely connected to the liquid-tight flexible metal conduit and to the grounding system at both ends. Loose connections can create high-resistance paths, impeding the flow of fault current. When using AC cable, verify that the cable is listed and labeled for the intended application. Using unlisted or improperly labeled cable can violate code requirements and compromise safety. Additionally, ensure that the AC cable connectors are properly installed and tightened. Improperly installed connectors can damage the cable and create a fire hazard. One potential pitfall to avoid is mixing different grounding methods. For example, do not run an external equipment grounding conductor in parallel with the metal armor of AC cable. This can create circulating currents and potentially overheat the conductors. Another pitfall to avoid is using improper grounding connectors. Always use connectors that are listed and labeled for the specific type of conductor and enclosure being used. Using improper connectors can create loose connections and compromise the integrity of the grounding system. It's also important to avoid damaging the conductors or insulation during installation. Damaged conductors can create short circuits and pose a shock hazard. Damaged insulation can reduce the ampacity of the conductors and increase the risk of fire. When working with electrical systems, always follow safe work practices. To energize the circuit before working on it, use appropriate personal protective equipment, and inspect all tools and equipment for damage before use. Remember that electrical work can be dangerous. If you are not qualified to perform electrical work, hire a licensed electrician. A qualified electrician has the knowledge, skills, and experience to perform electrical work safely and in accordance with the National Electrical Code. Now let's discuss some advanced considerations related to grounding and bonding. In some situations, it may be necessary to supplement the equipment grounding conductor with additional bonding conductors. For example, if the Liquatite flexible metal conduit is used to connect two pieces of equipment that are located a significant distance apart, it may be necessary to install a bonding jumper between the equipment enclosures to ensure that they are at the same potential. Bonding jumpers are typically sized according to National Electrical Code Table 250.102. In industrial environments, it may be necessary to use special grounding techniques to mitigate the effects of electrical noise. Electrical noise can interfere with the operation of sensitive electronic equipment and can even cause equipment damage. One common technique for mitigating electrical noise is to use isolated grounding systems. Isolated grounding systems separate the equipment grounding conductor from the normal grounding system, preventing noise currents from flowing through the equipment grounding conductor. Isolated grounding systems are typically used for sensitive electronic equipment such as computers and medical devices. Another advanced consideration is the use of surge protective devices, or SPDs. SPD are designed to protect electrical equipment from voltage surges caused by lightning strikes, power line switching, and other events. SPD divert surge current to ground, preventing it from damaging sensitive equipment. SPD should be installed at the service entrance and at branch circuit panels to provide comprehensive surge protection. When selecting SPD, it is important to choose devices that are properly rated for the voltage and current of the electrical system. It is also important to install the SPD in accordance with the manufacturer's instructions. Grounding and bonding are complex topics that require a thorough understanding of the National Electrical Code and electrical theory. If you have any questions or concerns about grounding and bonding, consult with a qualified electrician or electrical engineer. Remember that proper grounding and bonding are essential for electrical safety and equipment protection. Let's delve even deeper, exploring the nuances of applying these concepts in various real-world scenarios. Consider a scenario where the Liquatite flexible metal conduit is installed in a wet location. In this case, it is crucial to use fittings that are listed for wet locations. These fittings are designed to prevent moisture from entering the conduit and corroding the conductors. It is also important to ensure that the equipment grounding conductor is protected from corrosion. One option is to use a copper conductor with a moisture-resistant insulation. Another option is to use a stainless steel conductor. In another scenario, the Liquatite flexible metal conduit is installed in a hazardous location. Hazardous locations are areas where flammable gases, vapors, or dust may be present. In hazardous locations, it is essential to use explosion-proof fittings and enclosures. These fittings and enclosures are designed to contain any explosions that may occur within the electrical system. It is also important to ensure that the equipment grounding conductor is properly bonded to the explosion-proof fittings and enclosures. In a commercial building, the Liquatite flexible metal conduit may be used to supply power to lighting fixtures. In this case, it is important to ensure that the lighting fixtures are properly grounded. The equipment grounding conductor should be connected to the metal frame of the lighting fixture. It is also important to ensure that the lighting fixture is securely mounted to the building structure. In a residential building, the Liquatite flexible metal conduit may be used to supply power to appliances such as refrigerators and washing machines. In this case, it is important to ensure that the appliances are properly grounded. The equipment grounding conductor should be connected to the metal frame of the appliance. It is also important to ensure that the appliance is plugged into a grounded receptacle. When working with electrical systems, it is always important to be aware of the potential hazards. Electrical shock is a serious hazard that can cause injury or death. To prevent electrical shock, always de-energize the circuit before working on it. Use appropriate personal protective equipment, such as gloves and safety glasses. Inspect all tools and equipment for damage before use. Arc flash is another potential hazard. Arc flash is a sudden release of electrical energy that can cause severe burns, blindness, and even death. To prevent arc flash, always wear appropriate arc-rated clothing and personal protective equipment. Follow safe work practices and maintain a safe working distance from energized equipment. Electrical fires are another potential hazard. Electrical fires can be caused by short circuits, overloads, and loose connections. To prevent electrical fires, always use properly sized conductors and overcurrent protective devices. Inspect all wiring and connections for damage. Keep electrical equipment clean and free of dust and debris. Grounding and bonding are essential for electrical safety and equipment protection. By following the National Electrical Code and safe work practices, you can minimize the risk of electrical hazards and ensure that your electrical system is safe and reliable. Now let's consider some additional points about inspecting existing installations and troubleshooting grounding issues. When inspecting an existing electrical installation, pay close attention to the grounding system. Verify that all metal enclosures and equipment are properly grounded. Check for loose connections, damaged conductors, and corrosion. Use a multimeter to measure the resistance between the equipment grounding conductor and the grounding electrode system. The resistance should be low, typically less than 1 ohm. If the resistance is high, there may be a problem with the grounding system. When troubleshooting grounding issues, start by identifying the symptoms. Is there a shock hazard? Are circuit breakers tripping frequently? Is there excessive electrical noise? Once you have identified the symptoms, you can begin to narrow down the possible causes. Check the equipment grounding conductor for continuity. Use a multimeter to measure the resistance between the equipment grounding conductor and the grounding electrode system. If the equipment grounding conductor is broken or disconnected, it will need to be repaired or replaced. Check the grounding connections for tightness. Loose connections can create high resistance paths, impeding the flow of fault current. Tighten all grounding connections to the proper torque. Check for corrosion. Corrosion can increase the resistance of grounding connections and reduce the effectiveness of the grounding system. Clean any corroded connections and apply a corrosion inhibitor. If you are unable to resolve a grounding issue, consult with a qualified electrician. A qualified electrician has the knowledge, skills, and experience to diagnose and repair grounding problems safely and effectively. Remember that proper grounding and bonding are essential for electrical safety and equipment protection. By following these tips, you can help ensure that your electrical system is safe and reliable. Always prioritize safety when working with electrical systems.